Hello, everyone. Hope you're doing well. Today, we get to start answering some of the questions that we posed from the last video lecture from last week, namely the one where we started introducing Fourier series, talking about after we've now kind of introduced the concepts of uniform continuity and uniform convergence. We're going to answer some of our questions regarding the latter concept. Is it true that when you have a uniform convergence of functions, and sometimes you will see people write this f sub n converging uniformly by writing two arrows like this to mean that the functions f sub n converge uniformly to f, we get to ask the question, is it true that the integrals of the f sub n converge to the integral of f? So that's what this sort of thing that we'll be trying to address in today's video is taking a look at these sorts of things. In particular, we're going to be looking at this in the context of series because we're looking in particular about how we can work with Fourier series in this particular way. So we'll see these things in kind of the context of looking at series of functions, but we could translate these as well to just a sequence of functions as well. We'll have a few examples today that we'll be looking at in our homework. Hopefully, you've noticed this through the course of the homeworks is that oftentimes what I ask you to do is to say, okay, try and show that some of the propositions are not necessarily, their consequences do not hold true if we change our conditions very slightly. For example, we'll have something in our homework that talks about if these f sub n converge to f pointwise, then the integrals don't necessarily converge. We've also talked about one of those examples last week as well. It may be good now that we know what these two concepts are of uniform continuity and uniform convergence to go back and take a look at that video from the last week, section 5-3, and see what you're able to glean from that and see if now you can now not only know why we're studying these things, but now connect them back, fill in the gaps of knowledge that we had of what these types of concepts were. See if that makes a little bit more sense now that we're at this point. But we are going to be looking at series a good bit more today. In particular, I'm going to be utilizing a few of the series tests and things that we've talked about from our very beginning at this course back in week one. A few of the important ones that I will be bringing back in every now and then, either here or in our homework, are things like the geometric series test. If you have something like 1 plus x squared plus x cubed plus so on and so forth, then this series converges if the absolute value of x is less than 1. And if it's absolute value of x is less than 1, then what this converges to is the value of 1 over 1 minus x. And essentially, the way that you kind of get there is you say, okay, the way that you could rewrite any partial sum of this sequence, like say, for example, 1 plus x squared plus x cubed, is you could think of this as being multiplied times something like 1 minus x and ask the question, what happens if I go through and multiply these two quantities together? Well, what you end up getting from that is something like this. If you go through and just multiply things out, then a few terms are going to cancel. For example, x times 1 minus x times 1. All of the x terms are going to cancel. Similarly, all of the x squared and x cubed terms cancel, and all you're left with is 1 minus x to the fourth after multiplying all of this out. And what that gives us is that the 1 plus x squared plus x cubed quantity can be rewritten by dividing both sides of this equality right up here by 1 over x. So this is 1 minus x to the fourth divided by 1 minus x. In general, if you have a partial sum of this geometric series of the form 1 plus x plus dot 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 plus x to the n, then this can be rewritten as 1 minus x to the n divided by 1 minus x. And if I start taking limits of each of these things as n goes to infinity, then due to the fact that we're making a condition here that the absolute value of x is less than 1, the value x to the n should go to 0, so that all that we're left with in this limit is 1 over 1 minus x. So that kind of gets us to where we were looking at from before, that a geometric series should converge whenever the absolute value of x is less than 1. It's kind of a good kind of touchstone of what the sorts of things that we were talking about from before. If it helps, go back and review some of the quick word on series definition talks that we did back in video lecture 1-2, just to kind of get a brief overview of what series are again, as we will kind of pick up on some of those topics here as we go through it. We'll also mention again something called the alternating series test. So it might be good to kind of take a look back at what that test is. But trying to connect our notion of uniform convergence to how these things work in metric spaces, we do have a proposition that tells us how we can rethink of uniform convergence in terms of a distance function on the space of continuous functions. You may remember that on the space of continuous functions for C01 that we defined a metric given two functions, say f and g. Can't get the comma there. F and g inside of C01, then we would say that the distance between those two functions is equal to the supremum over all x inside of 0, 1 of the set of all values of absolute value of f of x minus g of x. Basically, this is saying that you're looking at every single difference between points of the function at the same x value. You're looking at all differences in y values at the same x value. You're saying that the supremum, the greatest lower bound, or the least upper bound of these distances is the distance between these two functions. That get defined for us a metric, and we went through and talked about why that was the case. And notice that essentially what we're saying here is a very similar thing to what we do when we say something converges uniformly. Because recall our definition of convergence uniformly is this: for all epsilon greater than 0, there exists a delta greater than 0, such that for all x and y, or rather, and I was doing uniform continuity without recognizing it. Should have written here that there exists an n in the natural numbers, such that for all x in 0, 1, and then for all n in the natural numbers, rather for all n greater than n, should be writing that instead, that it should be the case that the absolute value of f sub n of x minus f of x is less than epsilon. Now notice the combination of things that are put right here that I've underlined. Combining for all x inside of 0, 1 and this other statement, the absolute value of f sub n of x minus f of x is less than epsilon, you might recognize that we could actually combine these two statements into one. Because this is true for all x inside of 0, 1, then it has to be the case that the supremum for all x in 0, 1 of this absolute value of f sub n of x minus f of x is also less than or equal to epsilon. Now, we actually can just say less than epsilon due to some properties here about compact numbers, but you could certainly say less than or equal to by just taking a supremum of a bunch of values that are less than epsilon. You might think, can any of those values limit to epsilon? And you might want to put equals there instead, but we don't have that issue here. So this ends up combining these two statements together. Essentially, what we're saying is that for all n in the natural numbers, or for all n greater than n, the supremum of the differences between functions f sub n and the limit function f is less than epsilon. One final way we could go through and rewrite this is by using the definition of what we know the metric is in C01. This is exactly the definition of the metric between f sub n and f, that this is less than epsilon. And now looking at this definition, we notice something that this looks very similar to. This looks exactly like saying that f sub n of x converges to f of x in the metric for C of 0, 1. So these two ideas are exactly the same. You may not have recognized that this is the case when we went back and did these sorts of convergences back in week 3. We mentioned how there were certain like D infinity metrics in which something may not converge, but maybe it converges in D1 or D2 or something like this. This is an example of what it means to converge in the D infinity metric, or converge in what we've defined the standard metric on C01 to be. That convergence is exactly uniform convergence of functions. So to make that clear, the D infinity that we talked about back in week 3 is the same thing as uniform convergence. So if something in D infinity, if this goes towards 0, this is exactly the same, the uniform convergence of f sub n to the function f. So this is saying that these two concepts are identical, that we could rewrite the kind of quantifier statements of each of these two statements to be exactly the same. That's important to us, to be able to know what it means to converge inside of continuity, continuous functions. And this also kind of confirms our suspicion of what we talked about when we had this D infinity, is that D infinity convergence should be pretty hard. And that's similar to how we think of uniform convergence as well. Uniform convergence should be hard. It's a tricky thing to get a hold of because it's something that has to be true regardless of your values of x. We went through very many examples where our functions don't quite converge uniformly to a function, either because our f sub n are bounded and the limit function f is unbounded, or maybe we just don't have even convergence throughout the entire function. There's always something that's hanging up above an epsilon value of 1/2 away from the original function, like in the case of the x to the n examples that we did in the previous video lecture. So there's a lot of examples that kind of show pointwise but not uniform convergence. So having these examples at bay should tell us that uniform convergence is very strong. And that's similar to our suspicion that d-infinity convergence inside of C01, that is also strong. These are very strong statements. And when we have statements this strong, there's a lot that we could say about the functions and their limit points. And that's exactly what we're trying to talk about here today. This is a little bit of that proof. I've kind of gone through and already discussed this. If you want to go through and kind of pick it apart little piece by piece, then I've written how I would have gone through and talked about this here in this slide. But I've already kind of given a good enough explanation, I think, for this type of convergence. Now, note that a good question we could ask is, if the original functions f sub n that you have converging are continuous functions, is it the case that the limit of those functions is continuous? Let's go ahead and write that out. If the functions f sub n are continuous and f sub n converges to f, is f continuous as well? If the sequence of functions f sub n are continuous and they limit to another function, which we know very little about, could we conclude just from those pieces of information that f is also continuous? Is continuity preserved under pointwise convergence is essentially another way of saying this. Preservation means if I had something to begin with and I knew that the limit of these was some other function, then I get to carry over this property from the limiting functions to the limit function. And you can kind of see that I've already spoiled this down here in this slide, which is that continuity is not generally preserved by pointwise convergence. And we can see this through an example of something we've already talked about. Remember that we wrote this graph here for functions x squared, x cubed, x to the fourth, essentially the set of the sequence of functions f of x is equal to x to the n. And we saw that the pointwise limit of this function was this. All points for x values less than 1 for this function defined on the closed interval from 0 to 1 should get us to 0. But at x equals 1, it makes a jump. The limit function here makes a jump all the way up here to the point 1, comma 1. Recall that we said this because for any point less than 1, this is that geometric series that we were just talking about. That should limit down to 0 because the x values are going to go all the way down to 0. Think if a series converges, then the individual terms of the series have to go to 0 in order for the series to converge at all. But at the point f of 1 here, then I'm looking at 1 to the n, which is equal to 1 regardless of the value n that I work with. And so because of this, at x equals 1, my limit function is going to have a y value of 1. Note that I have found a discontinuous limit function from a sequence of functions that are completely continuous. So it is absolutely possible to take a sequence of functions and look at pointwise convergence here and get a discontinuous function instead. But we could ask this question. What happens if the f sub n are continuous and we have a uniform convergence of f sub n? And that ends up to be a different story. The answer to that one is yes. Your function is continuous with uniform convergence. Let's think a little bit as to why before we get into any sort of proof. Let's get some intuition as to this. Recall the difference between continuity and uniform continuity. Going back, convergence and uniform convergence. See, I get those mixed up as well. That's why I caution against that sort of making sure to separate those two when I talk about it. But the difference between convergence and uniform convergence is that convergence can happen just at any given point. So you can almost imagine that, like what's happening with this example is that at any particular slice, all of these points to the left of 1 are going all the way down. They're continuing to stretch all the way down, while this point right up here is getting held in place. So what you can imagine is at each point, what you're doing is you're stretching the function, you're stretching the function, you're stretching the function, and in the limit, it snaps. The function no longer is one continuous strand because all of these have been forced all the way down to 0 in the limit, and this point was stuck. exactly where it was the entire time. So there's a snapping going on. Now think about uniform convergence and ask the question, could that happen in a uniform convergence? Remember that that one says that you're always going to be, say this is a limit function f. Then what you're saying for uniform convergence is that there is going to be some sort of little epsilon window around these functions, around this limit function, so that wherever your function is, it's always going to have to eventually exist entirely inside of this window. So think this snapping process isn't going to go on. As I continue to let my epsilon go down to 0, this window down here is going to continue shrinking all the way down to the limit function. So there's no point to snap to make that discontinuity happen. Intuitively, that's the difference between continuity and uniform or convergence and uniform convergence, is that there's no possibility for a snap to go on. Notice also that because we have a continuous function here on a closed interval, that there's no place for us to go unbounded. And that also is going to help us make this sort of thing happen here as well. No snapping is going to take place here. So if you have f sub n, this sequence of functions that's in metric spaces that converges uniformly to f, and I should have added, if the f sub n are continuous functions, comma, then f is continuous. So this now makes a little bit more sense. We could absolutely have non-continuous functions that do not converge or converge uniformly to a similarly not continuous function. So that's a good addition there to make sure we have in this proposition. So going through and seeing what this argument looks like in terms of epsilons and deltas looks very similar to some of the compactness definitions that we've had. And I want to notice that, pick apart here that a lot of the arguments that we have seen before, even if they aren't verbatim repeated in some of these other proofs, many of the concepts are very similar. This epsilon over 3 argument, which is how I like to call arguments like this, which is that you're kind of breaking apart an epsilon into 3 different parts, and the 3 parts you're breaking it up into are, in some sense, their form is very similar. Then what you end up seeing here is that a lot of the same principles carry over from previous proofs to this proofs and how you go through and explain something. Let's think back to our picture before we get into this argument. Let's take again our limit function f and understand that any kind of limiting function eventually has to be inside of this little epsilon window. So asking the question, if these f sub n's that I have here in blue are continuous, how could I use that fact to prove that the limit function f is continuous? Well, what I do is I combine the fact that the f sub n are continuous and that f is uniformly continuous. The way I use uniformly continuous is that I know that there's going to be a epsilon over 3 greater than 0, for which I can get a delta greater than 0, so that my function f sub n and f are close. Oops, should have written n in the natural numbers again, because I should be writing this as uniform convergence, such that f sub n and n are close for all n greater than n. Essentially, what that does is that gives me a closeness here between not only this particular point between f sub n and f, but any other points there inside of the function. Now, to show that f itself is continuous, I need to be able to show that between 2 points that are close by. But I also get that same closeness at that point from that function point on the function f, and then the similar point on the exact same function f sub n, as long as this n value is greater than this cutoff point that I've already specified. Now, notice that I'm trying to figure out closeness between these 2 points. But I know that these 2 points are close to their corresponding functions on the function f sub n, and I know that the function f sub n is continuous. So I know that the corresponding y values on f sub n are going to be close to each other. So what I have is an epsilon over 3 argument. This can be epsilon over 3 close. This can be epsilon over 3 close. And then finally, the difference between the 2 y values on f sub n, I can make those epsilon over 3 close. And that's exactly what this argument is attempting to do, is to say if I add all those epsilon over 3's together, then what I end up getting to is an upper bound for the possible difference between these 2 points on the limit function f. I have a jump here, that's epsilon over 3. I have a jump here, that's epsilon over 3. And I have a jump here, that's epsilon over 3. Adding all of those together gets us to the epsilon that we want to be at the very end. So you can see here that that's exactly what we attempt to do here with this proof. And you can see me kind of write out some of those ideas in this proof. The important thing here is that because the functions f sub n converge uniformly to f, that it doesn't really matter what points that I'm using to guarantee closeness on the function f, because I can always get a difference between the corresponding y values on the limit function f and the limiting function f sub n to be within epsilon over 3. So that's exactly what I end up doing. The only thing I have to be careful of as I go through this proof is a consistency in my choice of delta. But you can see me go through and follow that closely here in this proof as I kind of work through this delta. Essentially, that's the main question I'm attempting to answer as I go through this proof, is how do I make sure my delta is chosen consistently? And it turns out to just be essentially I can get a delta from each of these that's consistent throughout any of the xy points that I have going from f and f sub n. And then for that particular function f sub n, I know the existence of a delta there. So I can choose essentially a delta that's the minimum between those two values. So go through that proof or read through that a little bit more, but that's a little bit of the idea behind the epsilon over 3 argument. I'll go ahead and write that over here, epsilon over 3 argument, because this is a classic case of this sort of thing happening, and maybe a way that's a little bit more clear to see than where we've started trying to use it in like some compactness arguments and things like that. Now we finally get to see where convergence and calculus combine. We've already seen that it's possible for areas under the curve to not be preserved under pointwise convergence. I said that in the correct English way, but I don't think that my text said that in the correct English way. It is possible that areas under the curve are not preserved. Okay, I did say that correctly. Very good. With the results about uniform convergence that we already have, for example, the fact that f sub n converge uniformly to f, that in fact f is going to be continuous, is it possible that the stronger definition can turn the tide? And the answer is yes. So let's take this f sub n to be a sequence of continuous functions converging uniformly to f. Then if we take the integrals of each of these functions, and notice how particular I'm being here. I'm adding limits now to make it a little bit more clear what I mean when I just write something like this, integral of f sub n converging to integral of f. That's to say that even in the definite form, looking at this going from a lower limit of a fixed point a to another point here of x, something in between the closed interval from a to b, that the functions here, f sub n, which are the integrals of these little f sub n, converge uniformly to the integral of f, the limiting function of the kind of the integrand functions that I have here. So essentially, this is the proposition that is what I was saying, but it's adding a few different limits to it to make sure that it's kind of clarified in that way. If f sub n converges uniformly to the function f, then that's going to imply that the integrals from a to x of f sub n is going to converge to the integral from a to x of f of t dt. And that this is true regardless of the x value that I'm working with here. What we're going to use in this is this proposition too, that the fact that f is itself a continuous function. That's going to be useful for us as we go through and build this proposition. So that kind of becomes a lemma for us as we start moving into this sort of thing. The big deal here is the fact that I can get a particular epsilon value that works regardless of the x value that I choose between the functions f of t and f sub n of t. That can work for the supremum of each of these things. And notice how quick and easy the proof becomes after I recognize that fact. Remember that all that I want to do here is say that basically that the functions of the integral of f of t and the integral of f sub n of t are going to be close enough to each other. And there's a little quick integral trick that I use here, and I kind of underplay it here in writing out the proof for the case of succinctness, but I want to kind of show it off here. It's this inequality right here. This inequality is an interesting move of the absolute value symbols. Do you see what happens going from one step to the other? On the left, I'm saying take the absolute value of the difference between these two capital F and f sub n functions. I'm just moving those in together to make it one integral in the step that comes prior. But the next step that I do is I say I can move the integral, which is just the absolute value of the area between the curves there, to make it less than or equal to the integral of the absolute value of the functions. Now notice that this is a positive value regardless, because the areas under the curve of an absolute value function are always going to be non-negative. No way I can get a negative area because my function is always going to be non-negative. So what is going to justify this absolute value thing inside of here? Well, think of it this way. The integral from a to x of f of t minus f sub n of t, this can have positive and negative areas. However, the integral from a to x of absolute value of f of t minus f sub n of t takes all of the negative areas and does what? Because the function in these negative areas, because there's an absolute value around it now, is going to be turned positive. That is going to turn all negative areas into positive areas. So I can actually use that as a justification to write a less than or equal to sign there. Similarly, if I think about all the negative areas, which become positive if I take the negative of this function, then all of those negative areas, well, there's some positive functions to those as well. So if I think about it this way as well, the negative of this, which turns all the negative areas into positive areas and all the positive areas into negative areas, well, I still have those positive areas now turned into negative areas becoming positive when I consider the absolute value of this function. And so for a very similar reasoning, I get this inequality as well. And these two inequalities together are exactly the fact that the absolute value of this quantity right here is less than or equal to the integral of the absolute value of these functions. I just combine these two facts together. And the reason behind them is that the negative areas are turned into positive areas. And here, the negative areas or the positive areas, which is equal to the negative of the negative areas, hence why we're caring about the negative on the outside here, that these become the negative of the positive areas over here. So these are essentially flipped back. Everything becoming positive means that regardless of how I think about these two functions, this is still going to work out. A quick thing to note here, just to kind of make sure as we're kind of in the stream of consciousness with this, is that this does not have to be a negative value. You could have more negative area than positive area. But the idea of why this is still greater than that value, even if this quantity over here is positive, is that the negative areas, which are now on top, are going to be added more to because now the positive areas, which are now at the bottom, when I take the absolute value, come back up to come into the positive region when I take the absolute value of this function. That's kind of what we're doing here with these inequalities. Putting those two inequalities together gets us exactly this. And this is a really cool fact about integration that you might want to use from time to time. It's a very neat thing. A little bit, it might be reminiscent to you of the triangle inequality if you think of this as like kind of an infinite sum of different parts of the function. You're taking the infinite sum and taking a look at its absolute value, and you're saying that's less than or equal to the infinite sum of taking the absolute value of each of the individual differences of each of the different function values in there. That can be a bit much to understand, but if you think of the integral as an infinite sum, this is kind of like an integral version of the triangle inequality. Now, that's actually all I need. That is the key part of this entire proof, because the rest of the proof is going to use the fact that I know that this f of t minus f sub n of t is always going to be bounded above by a constant function, and that constant function here is going to be epsilon over b minus a. So I really should have written epsilon over b minus a right here. So there that is. So because that is always true for any of the two functions, that's this function is less than or equal to this function. The integrals of those two functions will also have that less than or equal to equality. And hence, if I go through and integrate a constant function, the only thing that I'm doing is I'm multiplying by the difference between the limits, which is going to be x minus a. Well, because x is somewhere in between the interval from a to b, this is a value that is less than or equal to 1. So I can get a less than or equal to epsilon here. And connecting all of the different parts of this inequality gets me exactly what I need. Notice that this very short line actually had a good bit going on there. And so that's something that's neat and something we get to see a lot in these analysis readings too. I hope that you've been enjoying the reading assignments, especially as a way to connect with other people to help understand, okay, why was this inequality here? Or why did this sort of thing make sense? Or how should I be interpreting this sort of line? because seeing that again and again and through different people's perspectives helps bolster our understanding of what's going on mathematically in even short and simple proofs like this one right here. So this gives us a uniform convergence of f sub n going to f, where these capital F sub n and f are our integral functions. It's neat that we were able to get this from uniform convergence. Notice that that's exactly where we needed it right there, was the fact that we could do this for regardless of the value of x. So that this whole thing is bounded above by some sort of constant function. The corollary here is essentially what we've been dealing with. If you have f sub n, a sequence of continuous functions converging uniformly to f, then the integrals of those functions, f sub n, will converge uniformly to the function f of x. Now, quickly, the difference between these two things, looking back to where we were here. So here, f sub n was a sequence of continuous functions converging uniformly to f. And then this is saying essentially for any x naught, I didn't need to use just an endpoint of a at the very beginning, but I could have used any particular point as a base point here for the closed interval from a to b, that I still get a good integral there. And essentially that's what the proof is having to address, is that you could do this for any closed interval, even the closed interval from a to x naught. And that if you essentially do the argument on that and subtract that result, you end up getting this sort of corollary here. So might be good to just kind of take a look at that. But essentially, this is saying we could have redefined our functions entirely to be only defined instead of from a to b from x naught to b. But that might be too much work to just say, okay, we're going to restrict to this function. So we could just say, okay, well, we could do this at any given point for any base point x naught, not just the left endpoint of the interval where our function is defined. It's important to note, by the way, for each of these, even for the one with the x naught that we were looking at before, is that the functions that we have here are defined on compact intervals. Remember that we had a little example back in our previous video, a section 5-3 video, that is, where we had 1 over n, which is a sequence of functions that converges uniformly to 0. But if we looked at those integrals on an unbounded interval, that is, if we tried to integrate f sub n going from negative infinity to infinity, we did not get that this converged to 0 numerically, because the integral of 1 over n from negative infinity to infinity is infinity for all values of n. So it does not end up converging to 0. So that's exactly what's going on with these sorts of statements. You can even see me alter that type of function a little bit right here in this f sub n. Now, what we have down here is pretty neat. This is going to be a way of writing this in terms of series rather than sequences of functions. But this corollary actually comes directly from what we were just talking about. Recall that you can think of series as a limit of partial sums. So if I went through and defined f sub 1 equal to, or rather f of 0 equal to a function like v sub 0 here, and then f sub 1 equal to v sub 0 plus v sub 1, and then f sub 2 to be equal to v sub 0, v sub 1 plus v sub 2, v sub 2, and so on and so forth, then I know that the sequence f sub n is going to converge uniformly if this series converges uniformly. If we haven't given a good definition of a series converging uniformly, this is exactly what we could use. It's the sequence of functions that serve as partial sums of these sums of functions here. V of 0t, v of 0t plus v of 1t, so on and so forth, all added together. And that gets us a sequence of partial sums. For this series to converge uniformly, we're asking for the partial sums to converge uniformly. But now that we've written this series as a sequence of functions, then this follows automatically, because now we have a sequence of functions that converges uniformly to some sort of limiting function, which we call the limit of the series. And so we can apply exactly the propositions that we applied up before, using any base point x naught and going to any point x inside of the integral from a to b. We can now say that the way to write these integrals, right, is to say, okay, we'll just take a limit of the integrals of the individual functions themselves. Well, the way that each of these individual functions is written is, well, for example, if you look at some of these partial sums, you're looking at the integral from x naught to x of things like f sub 0 plus f sub 1 plus f sub 2. And even though that's a sum on the inside, if you're looking at these limits of individual functions, you could even bring the sum on the outside, like you do right here. Basically, connecting all of those things together, if you have a limiting series that you're taking the integral of, it's okay to think of that integral as a limit of partial sums. And because partial sums have only finitely many terms being added, you could just take the summation symbol outside. And if you can take the summation symbol outside, then you can take the limit on the outside, and that gets you a limit of integrals in your series. Notice the difference between the two things going on here. This right here is an integral of a limit of functions. And that this over here on the right-hand side is the limit of a sum of integrals. In fact, if you want it to be, it's for partial sums in particular. The integrals themselves are what are being summed. You integrate each individual function in the types of v sub n that you're working with here. And if you take and integrate each of those functions and add those together and take a limit of their partial sums, then that's what you end up getting. An example here of what's going on is taking something like, okay, take a sum of something like, let's say we're taking the integral of x over n squared. And let's say that we're doing this as x goes from 0 to 1. Then if we know that this integral of x over n squared converges uniformly to a particular function, then what we end up saying is that, okay, let's say, for example, that I get that this is the sum as n goes from 0 to infinity here. I believe that this, well, I can't actually write n equals 0 here because that would give me a 0 in the denominator. If I write this sum, then I believe that this is going to converge uniformly to a function a little bit like pi squared x over 6. So if I know that this convergence is uniform, then what happens is if I want to integrate, say, x naught to x of the function n equals 1 to infinity of t over n squared dt, only thing I did was I changed, so I had an integrating variable of t since I'm using x over here. Then I could rewrite that as an integral from n goes from 1 to infinity of the integral from x naught to x of the functions t over n squared dt. And what's interesting about that is this. Maybe I don't quite know how to very nicely integrate whatever my limiting function is over here on the right-hand side, but I do know how to integrate these individual functions that I can go through and integrate. Maybe it's easy for me to go through and integrate those. And if that's the case, then this is a much easier way of writing exactly the same integral. Because if I can calculate each of these integrals, then I get a series to go through and write. If I can say, okay, well, this is just n squared can come outside, so this is the integral of t, so it gives me t squared over 2, then I can just say, okay, well, this is going to be the sum as n goes from 1 to infinity of, what is it, t squared over 2, evaluated from x naught to x, times the function 1 over n squared. And if I go through and evaluate this, then I'm like, oh, wait, that actually gets to come outside of the sum, and I can just do some other types of sum things to kind of try and make that work. What that has me doing is simplifying the whole process of trying to integrate or maybe try and find the integral of a series of functions. So if it's harder to find the series than it is to find the integral of the individual functions, then I might opt to just take the integral of the functions first. And that comes very much in handy. In fact, do we have the example coming up next? No, we have the proof, but you may remember this example from before, which is the Fourier series here, which is going to essentially say exactly that, that this seems like something that's very tricky to go through and integrate the entire series of, but it's very easy to go through and integrate each of the individual terms of this series. So we'll talk about that example once we get closer to it. But this proof of the series commuting is essentially the same idea of what I was communicating from before. But I like to kind of show these sorts of things for those of us who are readers, because that helps us kind of build our intuition as well. Some of us are like, okay, well, I want to just see this in basically in the layman's terms of how I'm connecting it back to the previous proofs. But this is a way that we could just write this sort of proof in this sort of way. So first, essentially, is the main idea of this proof, which is given right here, which is that series are just sequences of functions, s sub n of x, being the sum going from 0 to some capital N of these individual functions, which I really should have written v sub little n right here. So if these functions converge uniformly to v of t, right, then that's going to mean, I suppose that I just kind of wrote this guy over here. I wasn't quite feeling it here. So this sum is x of x naught of x of the series is going to be equal to the limit of these partial sums. Well, thinking about what those partial sums are, they are finite sums of these functions, v sub little n. So if I rewrite s of n in this way, then what ends up happening is I can take a finite sum out of an integral no problem, because I'm always able to say that the integral from f of g is equal to the integral of f plus the integral of g. And I can repeat that step a finite number of times if I need to. The trouble is trying to repeat it infinitely many times. But I can always say, okay, break apart a finite sum into a couple of different integrals like that. Then, now that I have the limit outside for each of these n values, this should be a capital N as well. Oh, are you not wanting to work with me today? Let me charge my pencil for a little bit then. So once I bring that sum outside, I now have a limit out here. This should be a capital N right there. And this finite sum of n goes from 0 to n. And notice that these combine to be exactly the series, because this is a limit of partial sums now of integral values, of numerical values of this function. So this is a neat way to kind of connect these two concepts. Let's go ahead and see this in an example here with that same example of what we were working with from before, looking at the Fourier series of f of x equals x on the interval from -2 to 2. Remember again that we could rewrite this cosine of n pi as -1 to the n, and I'll do so here in this problem. To find the Fourier series of f of x equals x squared. What we do here is we begin the problem by saying, okay, well, I'm going to first try and get this to look a little bit different. So let's kind of give us a little bit more space here by coloring this out. So in order to figure out how to get x squared from this, what we might consider doing is, since this whole series is equal to x, we might try integrating both sides of this function. Since x is equal to the sum as n goes from 1 to infinity of -4 and -1 to the n pi, times sine of n pi over 2, x over 2, is I might try and go through and integrate both sides of this function. So this is the integral for x is equal to the integral of the sum as n equals 1 to infinity of -4, -1 to the n over n pi sine of n pi x over 2. Now, this uniform convergence happens by the alternating series test. You might notice that this -1 to the n going on here, that's flipping the polarity of each of the individual terms. And if you get something like this, where essentially the absolute values of the function are decreasing as you move along, which is absolutely happening here, at least in absolute value, you have that these sequences end up are decreasing and converge towards 0 a little bit. Now, there's a little bit of a nuance there because some of these sign values actually just evaluate to 0, but if you just take a look at the odd values of n, then those still are decreasing all the way down in absolute value. Then once you get to that point, what happens is you can say, okay, alternating series test happens here. So this is actually uniform convergence of these two functions. And by our previous proposition, then we know that this is the sum as n goes from 1 to infinity of the integrals of each of these functions. Note that the -4 and -1 over n and pi can actually come outside of this integral, since this is an integral with respect to x. That's exactly what's happening over here as well. The left-hand side is just x squared over 2 plus some sort of constant c1. And all I'm doing here is just integrating the value of sine n pi x over 2. Reminding ourselves briefly about what we do here, we have a little u substitution. So u is equal to n pi x over 2. So this gives us that du is equal to n pi over 2 dx. And remember, we have to divide by that particular value when we calculate this integral. The integral of sine is negative cosine, so that's going to get rid of this negative right out here and make it a plus. So you'll see in my next line that that negative goes away. So I'll have 4 times -1 to the n divided by n pi, and that's going to be times 2 over n pi again, the value of cosine n pi x over 2, and that's going to be plus c2. So that's what we end up getting for this one. We can go through and simplify a few things inside of here. One of the things that we could go through and simplify now is the fact that cosine n pi x over 2 is the kind of function that we're working with, but we do kind of want to try and figure out what this constant is. Perhaps we go through and plug in something that makes cosine equal to 0 here to make that a little bit easier for us. Let's try plugging in something like x is equal to 1. If we do that, then on the left-hand side, we have that this is 1 squared over 2 plus some constant, C1. And then that's going to be equal to, just kind of multiplying everything together here, I'll have 8 times -1 to the n over n squared pi squared of cosine of 0 now, because I'm plugging in something that makes this cosine value equal to 0 here. Actually, let me check and make sure that I'm doing that. This is for different values of n here. So looking at this again, I recognize that I have done the kind of the equivalent of forgetting my plus C. I've remembered the constants, but I forgot to carry over my series symbol. So actually, I have a whole series of values over here, which change with respect to this value of n. Because of this, I can't just necessarily say that this is cosine of 0. So that's a little bit, makes things a little bit crazier in order to find what this constant is equal to. I might now opt to choose a different value of x just to make things a little bit easier on me. But it kind of depends on what I'm more used to. X equals 1 actually does still work here very well, but I noticed that with x equals 1, I'm still going to have some values of x for which some values of n now, that is, so that cosine of n pi over 2 is not equal to 0. For example, if n is equal to 2, this becomes cosine of pi, and I'm looking at a negative value here for n. Now, there is actually a way to kind of continue on here. But I think it's best for us to think about this in terms of x equals 0 instead. So I'm going to go through and write this with x equals 0 and take a look at 0 squared over 2 plus c1, which is equal to, now, if I plug in x equals 0, this is cosine of 0, which is going to be equal to just 1 right here. And I'm looking at the sum as n goes from 1 to infinity of this value right here, of 8 times -1 to the n over n squared pi squared. And now we can just start taking a look through and figuring out some convergence theorems for individual sequences of source series to figure out what this value might be. There are some neat little tricks here that you might be able to look up with online, but for now, I think it's totally okay for us to kind of just say that this is the constant that we're looking for this function. So just kind of leave it here in this series. This does have a closed form. I'm just not going to go through because that's not kind of where we're trying to go with this particular direction. But at the end of the day, if we say that that's equal to this constant C1, I notice I'm kind of ignoring the C2 here. I could have just added it on to this constant over here at this stage. Then I can say that x squared over 2 plus this constant is equal to the what? The sum of n goes from 1 to infinity of 4 -1 to the n over, or 8 rather, -1 to the n of n squared pi squared times the function cosine of n pi x over 2 plus this, or minus this particular or rather with this particular constant here at bay. And after going through and solving for x squared, then that should get us basically where we need to be to solve for that Fourier series. And the rest of it is just moving that constant over and then multiplying times 2, like we said in the last week's lecture. So just a neat way to see how you can now calculate a whole class of Fourier series because of something that you know about uniform convergence of these. In fact, there are whole classes of theorems that talk about how Fourier series in certain classes do converge uniformly, in which case you don't even need to use something like alternating series tests to make this work. You can just use some of these other stronger theorems. Now, in terms of our homework, I'm not having us calculate Fourier series. I'm not having us do this. I just kind of wanted to connect back to what we did back in our video lecture 5-3. So that's all that I kind of wanted to intend there, is to see that there is something very useful here for these types of integrations. But we'll stick to some smaller examples here where we get to use other types of tests to show some convergence of series. This is something more along the lines of what we might see on our homework, which is this problem right down here. Show that the sum, as n goes from 0 to infinity, of cosine of nx divided by n squared plus 1 converges uniformly on the real numbers. So how would we go through and do this? The interesting thing going on here is that, well, a few things are happening. Cosine of nx is something that is going to be a bounded function, undivided by n squared plus 1. So what we could do here is something called a comparison test. You may be familiar with this from series, and we may have even talked about it back in week 1, which is to say that if you know that these a sub n are less than or equal to b sub n for two sequences, a sub n and b sub n, then the same thing is going to be true for the series of those two functions, n equals 0 to infinity for each of those two things. So if a sub n is less than or equal to b sub n right here, then this is a comparison test between the individual sequences that constitute a series between those two sequences. So what are we doing here to kind of help make sense of this? This is a different type of form of basically being able to take this sort of notion where now I'm taking functions inside of this series, a sub n of x, and saying that these are going to be less than or equal to constant functions with respect to x over here on this side. That's essentially what the Weierstrass M test is. It's taking the understanding of the comparison test and saying, if I have a function in x over here, if I can say that each individual function, a sub n of x, is less than or equal to some sort of constant with respect to x, some b sub n over here. And if I know that this over here converges, then I know that these actually converge uniformly on the interval in which these functions are defined. That's a pretty cool theorem to be able to say that. And the reason is essentially where we're coming from with this being derived as a notion of what the comparison test is. If you want to see a little bit more of a detailed proof in that, it was in our reading assignment for this previous week. So the idea behind Weierstrass is to ask the question, does there exist a b sub n such that our functions a sub n of x are less than or equal to b sub n? And then we also ask the question, does the sum of the b sub n converge? Because if we get to answer yes to both of those questions, then we can say that the sum of the a sub n of x converge uniformly. So this is the parts that we are putting together here for the Weierstrass M test, because that's a very good way of thinking about this particular series and this problem. Note that for this problem, that there is a way to bound this above by some constant function with respect to x. And that's because the absolute value of cosine of nx, or anything that's just a cosine function, this is going to be bounded above by something less than or equal to 1. What that does is that implies that the sum as n goes from 0 to infinity of cosine of nx, that this is going to be less than or equal to, or an absolute value rather. So let me just be clear, it's kind of following along with what we're doing here. The absolute value of cosine nx over n squared plus 1 is less than or equal to 1 over n squared plus 1. So to be clear, these are the functions with respect to x. And notice that what we've been able to bound these things with is a function, a constant function here, b sub n, with respect to x. If it helps, just think of these as constants. These are values that only change with the values of n as they iterate through a series, not with respect to x. So like with the comparison test, I should have put some absolute values around in here just to kind of be clear with that. This is what's being asked for with the Weierstrass M test. Now we ask the question, does this converge? Does the sum of 1 over n squared plus 1, then goes from 0 to infinity, does this converge? Now, this does end up converging, and for this, we can now start using some of our classical comparison tests. What I can do is I can separate this out to just be 1 plus the sum as n goes from 1 to infinity of 1 over n squared plus 1. And what separating out that 0th term does is that it allows me to do a comparison test on the remaining terms. I can now say that this is less than or equal to sum as n goes from 1 to infinity of 1 over n squared. Now, remember, the way that I'm able to say that is that this has a larger denominator here, so this is a smaller number. And this has a smaller denominator here, so this is a larger number. So term by term comparison-wise, this series here must be bigger than whatever this series is over here. And that's exactly what I'm using for this point. But this series converges by p-test. The p-test, you may recall, is the one that says if you have a series of the form 1 over n to the p with any starting index here going off to infinity, in this case it'd have to be n equals 1, then this will converge if p is greater than 1, and it will diverge if p is less than or equal to 1. You may actually know the closed form of this series, that the sum of 1 over n squared is pi squared over 6. Maybe that one depends on how many YouTube videos you've watched about series and things like this. But this is the classical closed form of this. So does it converge? Well, yes. It's a series of positive terms. It's bounded above by 1 plus pi squared over 6. So even if we just know the closed form, then we can actually use the monotone convergence theorem here instead. So that's two ways to show that this thing is a convergent series. We either use the p-test, like down in here, or you use the fact that you know that this series converges to pi squared over 6, so this whole thing is going to converge to 1 plus pi squared over 6. We now get to invoke the Weierstrass m-test, which says that the original series that we are working with, this is the v sub n, that this sum converges uniformly. N equals 0 to infinity of cosine of nx divided by n squared plus 1 converges uniformly. So this is how we could go through and use the m-test in this sort of way. This is something more along the lines of what we'll see more in kind of working with these types of problems. Using things like the Weierstrass m-test is a big deal because it's a lot like the comparison test, where we are comparing functions to constant functions here. You might be able to notice why this sort of gives us some sort of uniform convergence here, and I encourage you to kind of look through the proof as to why the convergence here is indeed uniform for these series. But we've been doing this with integrals so far. So there's an interesting case about what happens here with derivatives. And it turns out that we need a little bit more here than just uniform convergence at one level or another. This sequence of sine of nx over n is something that's worth considering. Now, I have us actually go through and analyze this a little bit more in our homework, so you might be good to kind of take a look at that and compare that here with this particular example. But just to kind of briefly give a sketch of what these sorts of functions look like, note that for when n is equal to 1, the sine of nx over n function is just the function sine of x. Looks something like this. When n is equal to 2, the amplitude of these little waves that I have here shrinks. Here, the amplitude of these waves, that is how high or low they go from the x-axis, is an amplitude of 1. As n equals 2, this is sine of nx over 2, namely sine of 2x over 2. So these things are going to have amplitudes of 1/2 now. So notice that the farthest possible that these functions can get away from the x-axis is now shrinking linearly or reciprocally, inversely, by a factor of n. But something else is also changing. The fact that there's an n here inside of the sine of x means that the frequency of these functions is also getting speedier. What's going to happen to the slope in this case? The slopes, or the derivatives of this function, think the derivative of sine of nx over n is going to be, take cosine of nx times n, using a chain rule here, divided by n. These slopes are going to be defined by the function's cosine of nx. Notice that these functions have a very similar property here, where as you iterate n, the frequency is going to increase, making the slopes increase, but that there is no amplitude shortening to offset that slopes. These functions, in fact, as I'll ask you to show, do not converge to any function. So these functions, sine of nx over n, bounded above and below by constant functions, converge uniformly to 0. But the derivatives do not converge to any function. So uniform convergence is not enough to preserve something about derivatives in this case. So we need something a little bit more. And that little bit more comes from the fundamental theorem of calculus. You may remember that the fundamental theorem of calculus says that if you have functions that say converge uniformly, then you can start utilizing this integral stuff as long as you have a pretty decent base point. Let me make that a little bit clearer here by giving the proposition here. Let's say that the functions f sub n are differentiable functions, and let's say that the derivatives f sub n prime are continuous and converge uniformly to a function g. So notice here we're saying something about the derivatives of the function being continuous here. This is a little bit different than what we had in the previous example where we said, let's let these functions up on this level be continuous and converge uniformly. And then let's see if we can say anything about the derivatives. And this proposition says, actually, we don't get to say much going down in that direction, but we do get to say a lot about going up. If the derivatives are continuous and converge uniformly, then we can say something about the original functions f sub n that we were working with, that these converge to the function of that these converge to an actual function whose derivative is the limiting function that these functions converge to. So notice that kind of like interesting wordplay going on there. It's saying that actually we don't know a ton about what goes on as you take derivatives going down. And a lot of it is that just some of the types of things, the issues that we get with sequences like this are not easily reconciled. So you might notice derivatives are a little bit tricky here. And I've shown in class before when I teach Fourier analysis that there is an actual way to see how derivatives of Fourier series end up blowing up a good bit, that their series end up not converging at all, and saying that integrals actually work a lot nicer in this sort of way. And that this proposition reverberates that. So all our conditions now exist on the set of derivatives. If the f sub n prime are continuous and converge uniformly to some sort of function g, and what's more, we even have to add one more condition here, that there is a point such that the f sub n of x naught actually converges. And if I have these two conditions together, then the sequence f sub n converges uniformly to a function f, and what's more, f prime is equal to g. I want to encourage you to think about the connections here with the fundamental theorem of calculus as it's written. The fundamental theorem of calculus, at least the second part of it, typically reads that if you have these f sub n's going and converging to some, or rather, if you have a function little f and you take a look at its integral, then basically it's saying that if you take the derivative of the integral, then in some sense you come back to the original function. And this is exactly what we end up using here to prove this proposition is the fundamental theorem of calculus here. So there it is. That's the use of it right here, is taking something like f sub n of x minus f sub n of x naught and rewriting it as the integral of function going from x naught to x of f sub n prime. And if we know these f sub n primes converge uniformly to g, then I know that I actually get continuity at this level of x to x naught because I know that my function g is continuous. So as I close x and x naught closer together, I know that this function integral should be going toward 0. In fact, this also is giving me another neat formula, which says after I end up taking a limit here, I can get a neat little function f of x equals b plus this integral of g of t dt. Notice that is exactly here where I needed to be able to say that my functions f sub n of x converged at some specific point. If they didn't converge, I wasn't able to rewrite this in a particular way. So it might be good to go back now that we kind of have discussed this sort of integral derivative stuff and take a look back at these particular proofs and think, how am I supposed to connect each of these concepts with each other here? So the last thing that I want to go through and mention here is kind of connecting it here with this example. The series of the sum as n goes from 1 to infinity of log of 1 plus x over n squared converges to a real value for x greater or equal to 0 and converges uniformly, in fact, on the closed interval from 0 to 1. Let's use the formula and the proposition that we just used to try and work through this series a little bit. So let's try and show that the sum as n goes from 1 to infinity, log of 1 plus x n squared converges uniformly. Because it doesn't seem very obvious from the outset here at all that there's a good way to be able to sum the logs of a bunch of values, right? Remember that, for example, if you tried and rewrote this, if you have a sum of a bunch of logs, right, you could make it a product on the inside. But even then, it doesn't look very nice. You can have different values of n all being multiplied together. Getting a uniform convergence of that with still a log kind of wedged in there is a little bit tricky. So why don't we take a look at what happens with the derivatives of this function? Now, what prompts us to go toward the derivative route? Well, if I'm taking the derivative of each of these individual functions here with logs inside of them, I could start looking at 1 over these values of 1 plus x over n squared, which could become a really big deal because I'm not having to deal with a log type thing. Logs are a little bit tricky to go through and work with it. So let's go back to that proposition that talked about derivatives to see if we can now say something about this sort of convergence. The proposition about using derivatives does this. It says, assume that the derivatives of the sequence of functions that we're attempting to say something about in terms of their uniform convergence. Let's say that these derivatives are continuous and that they converge uniformly to a function. So let's see if we can do that. We also are going to need to say that there is a point x naught such that these sequence of the original functions, not the derivatives, the f sub n, converges. We can do that second part first, actually. So let's go ahead and do that. So we're going to use our proposition on slide 13 of 15. I write out of 15 here because I don't think it counts the title slide. So if you go through the PDF search bar, I think it'll have 16 slides on it, in which case you'd pick slide 14 instead. So the proposition on slide 13 asks us to do two things. The first thing that I'm going to do is I'm going to use the fact that I think that at x equals 0, I can show that this series of functions converges. Let's see what happens when I plug in x equals 0 here. And this becomes the sum as n goes from 1 to infinity of log of 1 plus 0 over n squared, which is the sum as n goes from 1 to infinity of log of 1. And guess what a log of 1 is? This is 0. This is the sum of 0 as n goes from 1 to infinity. So f sub n of 0 is equal to 0 for all n, which implies that this limit n goes from 1 to infinity of log of 1 plus 0 of x of 0 over n squared. It's going to converge to 0. So that gives us our first condition that's needed here. Here, again, we're using the fact that like the f sub n that I'm talking about here, that these are the partial sums. That allows me to think of these series as sequences of functions and gets me the chance to use that proposition and leverage it, even though I'm working with a series instead of a sequence of functions. So that's the first thing. The second condition asks us to take a look at the derivatives and ask, can I show the derivatives converge uniformly to a point on this function? So let's start by taking the derivatives of each of the points on this function. Now, let's start by just taking a look at the derivative of log of 1 plus x over n squared. If I take the derivative of this function, what I'm going to get is the derivative of log is 1 over 1 plus x over n squared. But I'm also going to get that this is multiplied by something else. I have to do a chain rule for the stuff that's inside here. Since I'm taking a derivative with respect to x, I'm only going to have 1 over n squared as the derivative of the interior of this. Combining everything together here, I'm going to get something like 1 over n squared plus x. Okay. So this gives me 1 over n squared plus x here. So this is going to imply, if I'm looking at each of these individual partial sums of this, f sub n of x, then this is going to be the sum as, or rather I should write capital N here, since I'm using lowercase n as an iterating variable for this sum, that I'm going from little n equals 1 to capital N, that this is the, looking at the derivatives of this, it's going to be just the derivative of the individual terms of this finite sum, that this is going to be the sum as n goes from 1 to infinity, or n, of 1 over n squared plus x. Now I'm asking the question, can I get this series to converge uniformly? Well, guess what? You may already see this here, but there's a Weierstrass M test going on. Because I can now go back and say, take a look at each of these individual functions that are being used here. 1 over n squared plus x. Note that our x values are on the interval from 0 to 1, which means that I can make this denominator smaller to get a bigger number, 1 over n squared. Since the sum of 1 over n squared converges, then we know that the sum of 1 over infinity of 1 over n squared plus x, which is again the derivatives of these functions, f sub n prime, that this converges uniformly to a function g. So because this converges uniformly, and note in particular, I'm not asked to show that this converges to a particular value. I'm just asked to show this uniform convergence, that it just converges uniformly to something. I don't really need to go through and specify what this function g is for this particular example. I just need to show that it converges uniformly. And I've just shown two conditions that helps me out here. The first condition is when I have that there is a convergence at the level of the function itself at a particular point at x equals 0. And I've also shown that the derivatives, that is for the partial sums of this series, that these converge due to the Weierstrass m-test. Combining those two things together gives us exactly the proposition. So now the proposition allows us to claim that the original sums here, n equals 1 to infinity, that this log of 1 plus x over n squared converges uniformly. And again, since I'm not asked to give what that actual function is, that's a check mark, that's a smiley face, that's a little box right here. And that gets us everything that we need for this uniform convergence. Now you could start playing around with some of these other propositions if you would like. For example, what happens if I integrate each of the individual functions here? Might be something kind of fun to play around with. So when I say in this other part, see if our other previous propositions would apply to this series, well, what other propositions that we talked about would apply now? We know that this series converges. So what about the integrals of these terms? If I want to find the integral of this sum, n equals 1 to infinity of log of 1 plus x over n squared, then I now know that I could just rewrite this as the sum as n goes from 1 to infinity of the integrals of log of 1 plus x over n squared. And although integrating log is not the best thing in the world to do, it does involve some partial sums and things like this, or not partial sums. It involves integration by parts. It still is going to be a lot easier than trying to integrate whatever the convergence of this function would be, right? So that can be a very useful tool to help us out in a lot of different ways, is just being able to integrate functions of this form. But my goodness, what an extremely like applicable day of working with actual types of functions in each of these types of scenarios. As was mentioned in the preface of our textbook, Chapter 4 is what we're kind of working through right now. And you may have noticed immediately that what we're working with is a lot more concrete than what we were working with back in Chapter 3. Chapter 3, a lot of the stuff that we were working with was just in general metric spaces, whereas here we are working with individual functions. We are working with series and showing that these series do things. Now, I'll tell you something from my personal experience of working through analysis. When I started with analysis, I really liked the theoretical stuff. That made sense to me because I was like, I can see the kind of threads that go on behind the scenes, and I really liked that. I was really bad at these functions. I was bad at this part. These are the sorts of things where I started thinking I have so much to juggle, or I don't know what proposition that I need to use. These calculations were the things that had become tricky to me after a while. But I think that oftentimes the story can be reversed. The really kind of like the sort of stuff that where you're trying to do things in a very abstract sense can be kind of hazy, but dealing with things that are real true to life calculations can be something that makes a lot of sense. So depending on what type of personality you are, one of these chapters might click more than the other. So hopefully this helps hone you in a little bit as we kind of keep progressing through here in chapter 4. But we've talked about a lot today, looking at integrals of series of functions or just integrals of sequences of functions, and together with how this kind of iterates with taking derivatives and showing uniform convergence at any sort of level. But that'll do it for me today. Thank you so much. Have a wonderful day.